Alright, so here we're looking to explain why does a raised to the 0 power equal 1. Alright, so first we're going to look at something not related to the a to the 0 power. I just want to look at a simple division problem. 5 divided by 5. Now, without going into too much explanation here, this is just equal to 1. And no big surprise, any number divided by itself, again with the exception of 0, any number divided by itself is going to be equal to 1. Now, just as 5 divided by 5 is equal to 1, so is 125 divided by 125. And again, this is not spectacularly insightful, and you may be thinking to yourself, why even bother writing basically the same thing twice? That'll just bear with me a little bit longer. There's not much more to this, but it does set up the following thing. So rather than look at 125 as its own number of 125, I'm going to instead view this as 5 raised to the third power. So 125 over 125 will really become 5 to the third divided by 5 to the third. Now, this is still one thing divided by itself, and so this will still be equal to 1, and okay, no big deal. Rather than look at this as a division problem, what we're going to do instead is look at this as a manipulation using the properties of exponents. Alright, so now we know that if we have, according to our rules for exponents, a to the m divided by a to the n, this is equal to a to the m minus n power. So basically, if you have the same base with different exponents being divided by one another, that's cause for subtraction of those two exponents. And so that's what we're going to use over here with this guy. Instead of looking at this as a division problem, we're going to look at this as an exponent subtraction problem. So now, from 5 divided by 5, we are at 5 to the third divided by 5 to the third. But instead of viewing this as a division, we're going to look at this as an exponent subtraction problem. So this is 5 to the 3 minus 3 power, which is equal to 5 to the 0. And we already know that based on what we saw back here, this is just one number being divided by itself, and so this is in fact going to be equal to 1. And that's really all that 0 power is telling us. It's just that this is a situation where a cancellation of exponents has taken place perfectly, so that this wound up being one number divided by itself, thus leaving us with the number 1. We're asked to solve the equation 5 times 2 to the x equals e to the 3x plus 1. When we see something like this, you'll see that there are variables in the exponents, so you'll start thinking, yeah, we should be using logarithms here, and you'd be correct. And you start seeing that there's an e, you think natural log is probably the way to go, and again, you'd be correct. So what we're going to do is start off by taking the natural log of both sides. That gives us the natural log of 5 times 2 to the x to equal natural log of e to the 3x plus 1. Oops. There we go. Now it is true the natural log of e will wind up canceling themselves out, so that leaves us with a 3x plus 1 here on the right side. On the left, there will be a strong temptation for a lot of you to want to move this x out in front of that natural log. But you cannot do that. The reason why is that the x only applies to the 2. It does not also apply to the 5. So instead, we're going to have to split this up using our properties of logarithms. So we have a multiplication happening between the 5 and the 2 to the x. So we're going to separate these into 2 logs. So we have natural log 5 plus natural log of 2 to the x. Once that separation is done, now it is totally okay for us to move that x in front of that natural log of 2. So we have natural log 5 plus x natural log 2 to equal 3x plus 1. Now we've got x's on both sides of the equation. That's really not ideal. So at this point we're just going to pick one side to get our variables on, and then we'll move everything else that doesn't have a variable over to the other side. At this point, the choice is completely up to you. I'm going to choose to subtract off the 3x from both sides. And then that means I'll also be moving that natural log of 5 over to the other side by subtraction. So we're left with x natural log 2 minus 3x to equal 1 minus natural log 5. This may not seem like much of an improvement, but there is a nice benefit here, and that comes from the fact that we've got both x's on the same side, so we can now actually go back to some Algebra 1 skills and factor it out. That would be considered our common factor. When we factor out that x, we're left with x times natural log of 2 minus 3 to equal 1 minus natural log 5. So now remember, the goal here is for us to get x by itself. That's what we're trying to do here. So the thing that's getting in the way of the x is this natural log of 2 minus 3. Oh, one other just point to mention here. That's the number of natural log of 2 minus the number that is 3, not natural log of 2 minus 3. The natural log of 2 is separate from the minus 3. So now, though, that's exactly what we're going to get rid of from the left side by dividing out by natural log 2 minus 3. And if we do it to one side, we got to do it to the other. And so that goes away from the left side, just leaving us with x equals 1 minus natural log 5 over natural log 2 minus 3. We're asked to solve the equation, the fourth root of x cubed minus 35. That fourth root minus 2 to equal 4. Alright, so we're solving an equation, so we want to try to get the variables on one side and everything else on the other if we can. We'll start off by moving the 2 over. So we add 2 to both sides, and we get the fourth root of x cubed minus 35 to equal 6. Now, there might be a urge for you to start busting out some more logarithms, whether that be natural log or common log, to help you solve this problem, because we'll be able to write this as x cubed minus 35 to the 1/4 power to equal 6. But actually, logarithms are completely unnecessary. This is not a problem with an exponential in it at all. Remember, exponentials are going to be defined to be things that have a variable located in the exponent. In this case, our exponent for the bigger quantity is 1/4. It doesn't have a variable in it, so we don't need a logarithm. We just need to remember how to cancel out a fourth root, or the 1/4 power, and we're going to do that by raising both sides to the power of 4. Right, so take this to the fourth on both sides, so that leaves us with x cubed minus 35 on the left side to equal, and 6 to the 4th power is 1,296. That was definitely something you'll probably have to punch in your calculator. Generally, people just don't go around memorizing 4th powers of things. If you are, more power to you. But that wasn't me. I had to punch into my calculator also. All right, now from here, again, we're going back to our getting the variable by itself and everything else on the other side. So now we're going to add that 35 over to both sides. So that's going to leave us with x to the 3rd equals, and 1296 plus 35 gives us 1,331. Right, again, our variable is not located in the exponent, so again, we do not have to use logarithms to solve this guy. We just need to get rid of that 3rd power, so we're going to do that by taking the cube root of both sides. So we'll have the cube root of x cubed to equal the cube root of 1331. So cubed and cube root will cancel themselves out to just leave us with x to equal, and the cube root of 1331 happens to come out to be 11. And so that is our final answer. You can always check that by plugging it back into the original equation, but it'll work. Here we're asked to solve the equation 7 raised to the 2n power minus 7 raised to the n plus 1 power plus 10 to equal 0. Alright, so this one is pretty ugly as far as solving an exponential equation goes. Now, we do see our variable n located in the exponent, so we will be using logarithms at some point. However, we won't be able to do it right away. And the reason we won't be able to do it right away is because these exponentials are being added and subtracted from each other. So we really need to figure out a way of dealing with this as it stands now and being able to turn it into something slightly prettier. Now, the trick here is to kind of reframe the problem. Instead of looking at this as an equation with exponentials, which of course it is also something that's able to be written as a quadratic. So we have 7 to the 2n. But I can also view this 7 to the 2n as 7 raised to the n squared. And we can do something similar to this 7 to the n plus 1 and write it as, well, still minus, that's not going anywhere, 7 times 7 raised to the n power. So we'd have 7 to the first power times 7 to the n, and then if we were working this backwards, if we have 7 to 1 power times 7 to some other power, in this case 7 to the first and 7 to the n, we would add those together, so that would give us 7 to the n plus 1. And then finally, we'd leave that plus 10 alone, and still equal to 0. Right, now, on the face of it, this may not seem like much of an improvement, but because we've managed to isolate these 7 to the n's, both in the first and second terms, I'm going to do a little bit of a substitution here to make the next step a little bit more visually apparent. I'm going to call 7 to the n capital A. You can pick your favorite letter of the alphabet. It doesn't even have to be the English alphabet. Feel free to go into Greek alphabet, Hebrew, Cyrillic, whatever you feel most comfortable with. But anyway, I'm calling 7 to the n A. So with that, this equation changes a little bit to capital A squared minus 7 times capital A plus 10 to equal 0. So now with that visual aid substitution taken care of, this should, hopefully at least, seem much friendlier to you than what we'd been looking at previously. And that would be a simple quadratic now. So here we're going to factor this bad boy out. So to get a squared, that's going to be a times a, with the 10 being positive. Right here, that just tells us we're going to have two of the same sign, in this case, two negatives. And we want factors of 10. That'll give us 7, so that leaves me my options of 1 times 10, or 2 times 5, and the winner here is going to be 2 times 5. So we're going to have a minus 2 times a minus 5 to equal 0. So now, that tells us that capital A is going to be equal to 2, or the capital A is going to be equal to 5. And this would be great if, in fact, we were asked to solve for capital A, but we weren't. We were asked to solve, in the original statement of the problem, for n. And we made this substitution here of n, or 7 to the n, excuse me, to be equal to our capital A. So we're going to have to undo that substitution now. So instead of a, we're going to have 7 raised to the n power to equal 2, or 7 raised to the n power to equal 5. Now that we've got the variable as isolated as we can for both segments of this solution to the equation. Now is the time we're going to use logarithms. You can use common log or natural log. If you plan on moving on to calculus, you're going to become much more used to seeing natural log, and so that's what we're going to use here. So we're going to take the natural log of both sides for this first one. So we have natural log of 7 to the n to equal natural log of 2. So we're going to move that n down in front of that natural log of 7. So that leaves us with n times the natural log of 7 to equal the natural log of 2. And then we're just going to divide out both sides by natural log 7. So we get n equals natural log of 2 over the natural log of 7. Or, then we're going to play the same game here with the 7 to the n equals 5. So we take the natural log of both sides here. And so we have natural log of 7 to the n equals natural log of 5. So again, we move the n out in front. So we have n natural log 7 to equal natural log 5. And then we divide out both sides by that natural log 7. So we get n equals natural log of 5 divided by natural log 7. So these are our two possible solutions to this equation, and they do both work. We're asked to solve the equation log base m of 16,807 equals 5 plus log base m of 7,776. The most interesting detail about this problem is the fact that the variable is not inside the logarithm, it is the base of the logarithm. So this might be a bit unusual here, but it's still completely viable as far as problems go. There's nothing inherently problematic with this setup. There's nothing illegal going on here. We're going to treat this more or less the same. We're going to try to get things with the variable on one side of the equal sign and everything else on the other. Since we've already got the log base m on the left side, I'm just going to move all of the variables over to that left-hand side. So we're going to subtract off that log base m of 7,776 over to the left side. So that leaves us with log base m of 16,807 minus log base m of 7,776, and that is going to be equal to 5. Right, now the benefit of having done that by getting the variables on the same side is now that we have log base m's on the left-hand side and only log base m's on the left-hand side, we can actually combine those two logs together because we have two logs of the same base being subtracted from one another. So what we can do now is collapse this down into a single logarithm. That gives us log base m of the 16,807 over 7776 inside of a single log, and all that is equal to 5. Now, that may not look like much of an improvement, but this really has helped us out a great deal in terms of utility, because the next move, what we're going to do is use the definition of a logarithm. And so we're going to take our base of our logarithm, which is m, and raise it to the 5th power, because again, this is based on the definition of a logarithm, and that's going to be equal to our 16,807 over 7,776. So now in order to get the m by itself from the m to the 5th is just to take the 5th root of both sides, or raise both sides to the 1/5 power. However you choose to enter that in to your calculator is entirely up to you. I'm going to take and view this as raising both sides to the 1/5 power because it's a little bit easier for me. Alright, so 5th root and 5th power are going to cancel themselves out. So that will just leave us with m. And now while the 16807 divided by 7,776 does not come out nice and neat, those are actually both fifth powers of something. As it happens, the fifth root of the 16,807 is 7, divided by the fifth root of 7,776 is 6. So we wind up with a value for m of 7/6. Now, we still have to abide by the restrictions placed on logarithms, meaning that we have to have a base that is a positive real number, which we do have here. So that's our solution. M equals 7/6. The rest to solve the equation log of a plus log of a minus 2 equals log of 24. So we're going to solve for a, and a's are already together on the left-hand side, so we're going to go ahead and use that to our advantage. Having multiple logarithms on one side in an equation is typically not ideal, so we're going to go ahead and combine those two together. So we have two logs of the same base being added to each other. That means we can rewrite this as a multiplication inside of a single logarithm. So this is going to be log of a times a minus 2 to equal log of 24. Now I'm going to go ahead and distribute that a through on the inside. So we're going to have this a to go to both the other a and the minus 2. So that leaves us with log of a squared minus 2a to equal log of 24. Now we're in a situation where we have one log equal to another log. What we're going to do is, it's got kind of a fancy name called exponentiate. And so we're going to use the base of our logarithms, which in this case is 10, since we're using common log. So we're going to basically take and have both sides as 10 raised to their respective log powers. Now the reason for doing that is the exponential base of 10 and the log of base 10 will cancel themselves out. So these will go away on both the left and right side, and so that leaves us with a squared minus 2a to equal 24. So now this is down to a pretty straightforward algebra problem. So we're going to subtract off the 24 over to the other side. So we're left with a squared minus 2a minus, we're left with a squared minus 2a minus 24 to equal 0. Alright, so we've reduced this down to a factoring problem. So to get our a squared, we're going to have an a times a. And 24 is negative. So when you have a minus sign here for our constant term, that's going to tell us we're going to have one of each sign, so one positive and one negative. And so we want to look for factors of 24 that will add up to negative 2. In this case, that's going to be positive 4 and a minus 6. Right, so now we just take and set each factor equal to 0. So if a plus 4 is equal to 0, we know a will be equal to a negative 4. And if it's the a minus 6 that's equal to 0, then we know a is equal to positive 6. Now, we've definitely solved for a, but we need to find all of the a values that will legitimately work in the original statement of our problem. And the original statement had log of a and log of a minus 2. And now remember, there's a restriction on logarithms. We're only allowed to have positive numbers inside of our log. So if a is equal to negative 4, that first term here would be log of negative 4, and that will be a deal breaker. So we cannot have the negative 4. If a equals positive 6, we're back up here. Positive 6 works just fine inside of our logarithm. And now we check for the next part. Log of 6 minus 2, that would be 4. That's also fine. So this is our only solution. A equals positive 6. For this problem, we're asked to solve log of 7 raised to the w power plus 29 to equal the natural log of pi minus 8EW. So on the face of it, this looks pretty unpleasant. Right, so if we're going to kind of just control the panic reaction that's possibly taking hold of you right now, we'll just follow the basic ideas behind our solving of equations. So we're going to get everything with a variable in it on one side and everything that's not got a variable in it over to the other. Now remember, E is a number in this case. That's Euler's constant, the 2.71 blah blah blah. So we will not worry about him as a variable. So our only concern are the w's. So we've got one here on the right side and one over there on the left. And I'm just going to pick the left side to get everything over to. So I'm going to add the 8EW over to the left side. And while I'm at it, we're going to subtract off the 29. So that'll go over to the right. That leaves us with log of 7 to the w plus 8EW to equal the natural log of pi minus 29. Okay, so we have a variable in an exponent, and we also have a variable that's down in the position we're used to seeing. So before we try to go real crazy here, we'll just use our properties of logs to move the w that's in the exponent of the 7 out in front of that logarithm. They've done us a favor by already giving us the logarithm to go with that. So now that leaves us with w log of 7 plus 8EW to equal that natural log pi minus 29. Right, so now we're just going to use our algebra skills here. We've got w that's present in both terms on the left side, so we're going to factor him out. So that gives us w times log of 7 plus 8e, and then that's still equal to our natural log pi minus 29. And then for our last step here, we're going to divide out the thing next to the w, which is our log 7 plus 8e. So we get w equals natural log pi minus 29 over log 7 plus 8e. And that's our final answer. This problem is asking us to solve the equation log base 3 of c plus 15 minus log base 3 of 1 minus c equals 2. And well, they've given us a variable on the same side. That's the left side in this instance. So that's somewhat helpful. The fact that they're inside logarithms is a bit more irritating. So what we're going to do first here is note that the logs are of the same base. We have both of these guys are of log base 3. And when we have two logs of the same base being subtracted from one another, we can combine them together in a single log. Subtraction will turn into a division inside that single log. So we have log base 3 of our c plus 15 divided by 1 minus c to equal 2. All right, now we're going to use our definition of a logarithm. So we're going to have 3 raised to the second power to equal whatever was inside of our log, which in this case was our c plus 15 over 1 minus c. Now, 3 squared is just 9 to equal our c plus 15 over 1 minus c. All right, now to kind of deal with the fact that we've got a c in both the numerator and the denominator, we're going to take and multiply both sides by that 1 minus c. So from here that'll give us, and I'll distribute the 9 through here, so that'll be 9 minus 9c to equal the c plus 15. And we'll go ahead and move the 9c over to the right side. So we'll add 9c over to the right. And while we're at it, we'll go ahead and subtract off the 15 over to the left. So 9 minus 15 will give us a negative 6 to equal our 9 and 1 will be 10c. Then we divide out both sides by 10. And we can reduce here just a little bit, so that leaves us with c equals a negative 3/5. Right, now you might be concerned by the fact that our c came out to be a negative number. But remember, it's not the fact that it's a negative number that's inherently bad for variables. We just can't have a negative number inside of our logarithm. So in this case, if we have a log base 3 of negative 3/5 plus 15, well, negative 3/5 is less than 1, so the fact that we're adding 15 is going to take care of any possible negatives there, minus our log base 3 of 1 minus our negative 3/5. And so negative times a negative will give us a positive, so this actually becomes 1 plus 3/5 here. And so that's going to be just fine for the logarithms also. So our c of negative 3/5 is our final answer. In this problem, we have a radioactive iodine isotope that's decaying according to the function a of t equals 14e to the negative 0.087t, where a is the amount of the radioactive iodine that remains in grams after t days. Part A asks us to find the amount of iodine originally present. This is not such a big deal for part A. All right, so if we're talking about something being present originally, that means that no time has passed. So what we're looking to do is find the amount at time 0. So we'll just plug 0 in for t into our equation, so that gives us 14 e to the negative 0.087 times 0. 0 is going in for our t. So e to the negative 0.087 times 0 is e to the 0 power, which is 1. So that leaves us with 14 grams if you want to be specific about it, but 14 is generally sufficient for these types of problems. But for part B, we want to find how much of our iodine is present after 20 days. So that just tells us that our time equals 20, so we put a 20 in for t. So we are looking to find a of 20. So that'll be 14 times e to the negative 0.087 times 20. Gives us e to the negative 1.74 power. Now all this just becomes a bit of plug and chug on the graphing calculator. So we'll put in 14 times e to the power of negative 1.74, and we get 2.457 when we are rounded to 3 decimal places, like the problem instructed for us, and that's again in grams. All right, for part C, we want to find how long it'll take for half of our original amount of iodine to remain. So we want to know when A is equal to 7. So we're actually going to be solving for t here. So we have 7 equals our 14 e to the negative 0.087t. Okay, so we're trying to solve for t, and that means we want to isolate t as much as possible. So our first step here is going to be divide out the 14 to both sides. So we're left with 1/2 equals e to the negative 0.087t. Now, with the e to the power of and something with a variable in that exponent, that tells us we're going to need to use logarithms here. So we're going to take the natural log of both sides. You could use common log if you really wanted to, but natural log is much more useful here as it allows us to cancel out the e on the right-hand side. So that leaves us with the natural log of 1/2 to equal negative 0.087t. Now I'm leaving this as natural log of 1/2 for the time being, so that I can just wait and do all my rounding at the final step without having to worry about any additional rounding errors creeping up from rounding too soon or too early in the problem. Alright, so we have our natural log of 1/2. Now we're just going to divide out both sides by the negative 0.087. And we discover t is equal to 7.967 days. And for this problem, we want to know how long it'll take for an investment of $100 to double at varying interest rates. So part A has the interest rate at 8% compounded quarterly. All right, so that's going to use a regular compound interest formula, which is A equals P times 1 plus R over N raised to the NT power. So A is the amount after compounding, P is the principal or starting amount of money, 1 is, well, 1. R is our interest rate. Remember, that's going to be as a decimal, though. N will be our number of times per year compounded, and T is going to be the amount of time in years. Now in this case, since we're looking for how long, we'll be solving for T, and that'll be true for each one of these three parts. So for $100 to double, that'll put the amount at $200 for part A. And so we'll start at $100 here with our 1 plus our interest rate of 8%. 0.08 compounded quarterly, so that'll be 4 times per year, raised then to the 4t power. Alright, so first thing we're going to do is just move that 100 over to the other side. So we're going to divide out both sides by the 100, and so that leaves us with 2 equals, actually while we're at it, let's go ahead and do the 0.08 divided by 4, so that'll give us a 0.02, so plus 1 will give us 1.02, raised to the 4t power. Okay, now the t is the part that we care about, and that's located in the exponent. So that means that we are going to be using logarithms to move that guy down. So we'll go ahead and take the log of both sides. All right, so we're left with log of 2 to equal, now we can move that 4t out in front of our log of 1.02. Alright, so now the t is down in a position where we can get to it algebraically. The only things that are in the way of the t at this point is the 4 and the log 1.02. So that's what we're going to divide out from both sides. That 4 log of 1.02. So let's go ahead and move this back up here to make it a little easier to look at. So we know that then t will be equal to log 2 divided by 4 log 1.02. So then we're just going to punch that into our calculator. Now the instructions here tell us we can round to 3 decimal places if necessary. And in this case, yeah, that's going to be necessary. So we punch all that in. And we discover t is equal to 8.751 years. Alright, so that's our answer for part A. Part B of this problem is going to proceed very similarly. So we have $100 going to double. So that'll be to $200 equals 100 times 1 plus. Our interest rate now was 6%, so that'll be 0.06 compounded monthly, so it would be 12 times per year compounding for our n, and then raised to the 12t power. Just like in part A, we're going to go ahead and divide out by 100 first. So we're left with 2 equals our 1, and 0.06 divided by 12 is going to give us 0.005, so this will be 1.005 raised to the 12t power. And just like before, the t is located in the exponent, so just like what we did in part A, we're going to take the log of both sides. And you can use natural log here as well. The choice is really up to you. And so we're left with log of 2 to equal 12t log of 1.005. And so we want to get the t by itself, so we're going to get rid of the 12 log 1.005 by dividing it out to both sides. So again, we just punch that into the calculator, and what we're left with here is t equals 11.581 years when we round to 3 decimal places. So there we go for part B. So now part C for this problem is a little bit different. Here we have interest rate at 7% compounded continuously. So that means we are going to use the, well, oddly enough, the formula for interest compounded continuously, which is A equals P times E raised to the RT power. A is still going to represent the amount after compounding, and P is still our principal investment. Now, instead of the whole 1 plus R over N business, we've got this E to the power of RT, and again, R is for our interest rate, and we are going to use that as a decimal. So the amount here would be $200. That would be a double of our starting value of 100. We have E raised to the 0.07t power. Just like in parts A and B, we are going to divide out by 100 first to get that term with a t by itself. So we're left with 2 equals e to the 0.07t. So now instead of using the common log like we did in parts A and B, I'm going to choose to use natural log here because that will get rid of the e forming, cancel that out from the right-hand side. So we're left with the natural log 2 equals 0.07t, and so to get t by itself, all we have to do is divide out both sides by the 0.07. And again, we're going to punch this into the calculator, and when we do that, we get t equals 9.9002 years. Well, okay, I rounded a little late. That's 4 decimal places and not 3, but that's okay. That'll give us to more accuracy, which will be fine. If we did just round it to 3 decimal places, that would be 9.900. You would have to have both zeros there for that. All right, for this problem, we have that the number of bacteria in a colony will grow exponentially over time. And if we know there are 75 bacteria present after 2 hours and 9,375 bacteria present after 5 hours, for part A, we want to use our formula here, n of t equals n sub 0 times e to the RT power to determine our formula for the number of bacteria in that colony. So we're also instructed that n sub 0 is to represent the number of bacteria present initially. And I think that's everything we're going to need to know about this problem. All right, this is promised to be challenging, and so it will be. So we don't know how many bacteria are present initially, and that's kind of important to our n sub 0 guy here. So that fellow's going to make the equation work, or at least part of it. So what we do know is that n of 2 equals 75, and that n of 5 is going to be equal to 9,375. So, okay. Now, each one of these is going to then fall into the same category here. So if we know n of 2 is 75, that means that 75 is equal to n sub 0 e to the r times 2, where t is our time, so that's going to be our 2. And similarly here for the n sub 5. And the 5 will be our 9,375, which will be equal to n sub 0 e to the r times 5 power. So I'm going to clean this up just a little bit to make it a little easier to look at. So we have our 75 equals n sub 0 e to the 2r, and then our 9,375 will equal n sub 0 e to the 5r. Alright, so now this is, I would call this irritating, because we've got these n sub 0s and r's both present in both equations, and so we can't directly solve either of the two equations for one of those two variables. But what we can do is use what we've got to kind of set up a substitution. So what I'm going to do here is I'm going to take and look at this first one here, the 75 equals n sub 0 e to the 2r. And I'm going to solve this guy for n sub 0. Now, this won't give me anything directly, but it will allow me to make some progress when I substitute it into the other equation. So if I want to solve for n sub 0, that just means I'm going to divide e to the 2r out from both sides. And so I have this kind of ugly expression, 75 over e to the 2r power to equal our n sub 0. So now what I'm going to do is take that guy here and substitute him in for the n sub 0 in our second equation. So what will happen there is we'll have 9,375 to equal 75 over e to the 2r times e to the 5r. Now the nice thing that does happen here is e to the 2r is going to cancel out with some of that e to the 5r, and will leave us with e to the 3r power. Remember, when we're dividing two things with the same base and different exponents, we just subtract those exponents from each other. So we had 5r minus 2r to give us that e to the 3r. So that's what we're working with now. 9,375 to equal 75 e to the 3r power. So now we divide out both sides by the 75. And we get e to the 3r equals 125. Alright, so now we want to get the r by itself, so we have to get rid of that e. So the way we're going to do that is by taking the natural log of both sides. So natural log 125 equals 3r. So we divide out both sides by 3. And we're left with r to equal the natural log of 125 over 3. Okay, that's not pretty, and I'm just going to leave this as is, because remember, I want to still find my n sub 0 as well. So now we're going to take that guy, r, and plug him back in the r in our n sub 0, and we've got then our n sub 0 will equal 75 over e to the 2 times natural log of 125 over 3. Now that's kind of a hideous expression, but we can make it a little bit more pleasant to look at here. We can write this exponent of e as 2/3 times the natural log of 125. It's not great, but it'll do for the purposes of punching this into our calculator. All right, and when we do that, we discover that n sub 0 equals 3. Now, there's a way we could have algebraically simplified that down. I'm not sure if anybody was really looking forward to doing that by hand or not. I'm willing to bet almost all students would just go right to the calculator to punch that in. So there we go for our n sub 0 and our 3. So now we're going to put all of that information together. Oops, I don't want to scroll that far. So we have our r and we have our n sub 0. So now we're going to put this formula together. So we know that n of t is going to equal our n sub 0, which is 3, times e to the r, which will be our natural log of 125 over 3 times t. So that is our formula, and that is the answer for our part A. So having gone through all of that to get our answer for part A, part B wants us to find out how many bacteria will be present after 10 hours. So this actually isn't so bad. Now we just have our n of 10, meaning we plug a 10 in for t. So we have 3 times e to the natural log 125 over 3 times 10. Nothing actually to solve for here other than just finding our value for n. So we're just going to punch that 3 e to the natural log 125 over 3 times 10 into the calculator. And what we discover for our answer is 29,296,875. Put the commas in here to make that a little bit easier to look at. And that's all we had for part B. That's the number of bacteria after 10 hours. So we're asked to use properties of logarithms to rewrite the following expression into sum or difference of logs. First, we have the natural log of the quantity y minus 4 to the 6th over 7 times square root of y squared minus 81. So this is a relatively irritating looking combination of things for logarithms. So start off first by just looking at this and saying, okay, so we've got a division of 2 logs. So we've got this y minus 4 to the 6th up here in the numerator, and we've got the 7 times the square root of y squared minus 81 in the denominator. Those are both inside of a single log, so what we can do is rewrite that as a difference of 2 logarithms. So we'll take this as the natural log of y minus 4 raised to the 6th power minus the natural log of 7 times, now instead of the square root of y squared minus 81, I'm just going to write this as y squared minus 81 to the 1/2 power. All right, now I can move the 6 in front of our natural log here in our first term. All right, so we can have this as a 6 natural log y minus 4. But I cannot do the same for the 1/2 in the second term. The reason for that is this 1/2 is only applying to the y squared minus 81. It is not also being applied to the 7. So before we can do anything else with that, I am going to have to make that split happen. Now remember, this is 7 times the quantity of y squared minus 81 to the 1/2, but because of the negative sign that's in front here, when I make that split happen, I'm going to have to think of this as negative, and then inside here we'll have our natural log 7 plus natural log of y squared minus 81 raised to the 1/2 power. And the reason for that negative sign outside of the brackets is the negative here from this guy. This applies to everything that's inside of this logarithm. So that's both the 7 and the y squared minus 81. So basically when we do the split, what we have to have happen is the negative needs to be able to go to both. So whether you write that out as a separate step as I've done here, or if you just jump right into this as 6 natural log of y minus 4 minus natural log 7 minus natural log of y squared minus 81 to the 1/2. Doesn't really matter if you do that intermediate step or not. I would urge you just to go with whatever makes the most sense to you. If you would prefer to just jump right in and distribute the negative as you go through here, like I've got, that's fine. If you prefer to not have to deal with that, that's also fine. Alright, at this point we can now move the 1/2 in front of that natural log of y squared minus 81. So that leaves us with 6 natural log y minus 4 minus natural log 7 minus 1/2 natural log of y squared minus 81. Now, at this point you might be tempted to think that you're finished, but unfortunately we are not. The problem lies with this fellow right here, the y squared minus 81. The reason there's a problem is that that guy can be factored further. So what we're going to do here is leave the 6 natural log y minus 4 and the minus natural log 7, leave them as is. And again, we are going to write the minus 1/2 natural log. And now I'm just going to put this in brackets to make this a little bit more apparent. Y squared minus 81 is a difference of 2 squares. So that's y minus 9 times y plus 9. And now since that's a multiplication happening inside of a single logarithm, that means we can rewrite this as follows. So we still have our 6 natural log y minus 4 minus our natural log 7 minus our 1/2 natural log of y minus 9. And again, because of the negative 1/2 being in front of the natural log back in our previous step here, what we're going to have to do is then distribute that minus 1/2 again to both parts of that separation and have a negative 1/2 natural log of y plus 9. Right, at this point we would look to see if there are any other things we can split or possibly even combine like terms, but we cannot. So our final answer is going to be this whole monstrosity here, the 6 natural log y minus 4 minus natural log 7 minus 1/2 natural log y minus 9 minus 1/2 natural log y plus 9. Or whereas to use the properties of logarithms to rewrite the following as a single log. We've got a pretty ugly looking mess of logarithms here. We have 4/3 log base pi of x to the 9th plus log base pi x minus 2 minus 1/2 times the quantity 8 times log base pi of x minus 2 minus log base pi of x plus 5 to the 6th. Now ordinarily I would be wanting to start using the order of operations and doing what's inside parentheses first. However, I do happen to notice that they've given us a log base pi of x minus 2 inside the parentheses here, and I've got a log base pi of x minus 2 happening outside of those brackets. So I'm actually going to go ahead and take that negative 1/2 and distribute him through first, because that'll allow me to combine like terms. So we'll take that negative 1/2 through to both parts. If you didn't spot this, it'll still work out. You'll just have a little bit of cancellation to do a bit later on in the problem. So that leaves us with 4/3 log base pi of x to the 9th plus log base pi of x minus 2 minus, so 1/2 times 8 will be minus 4 log base pi of x minus 2 minus 1/2 log base pi of x plus 5 raised to the 6th power. Right, so now that we've got all of that negative 1/2 distributed through, I'm going to combine my like terms here. So I've got a positive log base pi of x minus 2 minus 4 log base pi of x minus 2. And so the part that we're going to care about here are just the coefficients. Now there's assumed to be a 1 here in front of the first log base pi, and then I've got a minus 4. So we'll take that 1 minus 4, and that'll leave us with a negative 3 log base pi of x minus 2. Now the other components of this expression here, the minus 1/2 log base pi of x plus 5 to the 6th at the back end will stay the same, as will the 4/3 log base pi of x to the 9th out front. Right, at this point, I would love to be able to start to combine all of these logs together. However, that only works if I don't have coefficients in front of my logarithms, which I do in all three cases here. I got a 4/3, I got a -3, and I got a -1/2. So what we're going to do is we're going to take those coefficients and we're going to move those up into the position of exponents inside the logarithm. Now, for a couple of these, we've got exponents that are already present in addition to the ones that we're moving up. So what we're going to do is treat those just like we're taking a power raised to another power, and by that I mean we're going to multiply those exponents together. And what that'll look like here as a kind of transitional stage is we'll have log base pi of x to the 9th times 4/3, all up in the exponent here, minus log base pi of x minus 2 cubed minus log base pi of x plus 5 raised to the 6 times 1/2 power. Now I've just written these out here. I would assume most of you would just go ahead and do the multiplication either on your calculator or by hand. If you're doing it by hand, remember the 9 is going to be over 1, so the 9 and the 3 are going to cancel themselves out, so that leaves us with log base pi of x to the 4 times 3 is 12th power minus our log base pi of x minus 2 to the 3rd minus log base pi of x plus 5 to the 3rd power. And now that we're clear of all of our coefficients, now we really can start combining these three terms together. Now I'm just going to work left to right here. So I'm going to first just do the log base pi of x to the 12th minus log base pi of x minus 2 to the 3rd. So we have two logs of the same base being subtracted from one another, so that means we can rewrite this as a division problem. So this will become log base pi of x to the 12th over x minus 2 to the 3rd. And we still have the minus log base pi of x plus 5 cubed. So now we're just going to play the same game all over again. Now we'll treat our two logs of the same base being subtracted from one another as, again, another division problem. So that'll leave us with a log base pi of x to the 12th over x minus 2 to the 3rd. And then we would have that whole thing divided by the x plus 5 to the 3rd. But that's going to get a little bit ugly to write. So if we did that, let me make my bracket a little bit larger, we would have this whole thing over x plus 5 to the 3rd. But that's not what we would consider to be a completely simplified form. That leaves us with a complex fraction, so we really have to deal with that somehow. Now, it is kind of ugly, and nobody likes dealing with fractions more than they have to, but this isn't too terrible because the way that we've got this is we've got the x to the 12th over x minus 2 to the 3rd being divided by this x plus 5 to the 3rd. So now we know that dividing by a fraction is the same thing as multiplying by its reciprocal. So now while the x plus 5 isn't part of the fraction, it is still something we're dividing by. So we're going to go ahead and rewrite this inside of our bracket as log base pi of the x to the 12th over x minus 2 cubed times, now the reciprocal of x plus 5 to the 3rd is going to be 1 over x plus 5 to the 3rd power. And so then we can just put that all together through multiplication to leave us with a log base pi of x to the 12th over x minus 2 to the third times x plus 5 to the third. And that is our single logarithm. So that is our final answer.